Hello everyone, this is Brock Skaggs, and I'll make this video looking into spur gear trains. And so I've got the gear train that I'm going to want to analyze here inside of SolidWorks, and you can see the motion here will have a certain known angular velocity of the small gear here on the left hand side, and then as it rotates you can see the gears going in different directions through the train, and then we'll have it appears to be a smaller angular velocity once we get to this output gear here on the far right hand side. And so things we're going to ask is, okay, if I know the angular velocity of this gear here on the left hand side, can I calculate the angular velocity of the gear on the right hand side? And also, what are the center distances? And so by center distance I mean, say we take this gear and its shaft and axis that it's rotating about, and this gear and the shaft and axis it is rotating about. What is the center to center distance that needs to be had there, achieved in order to have these gears mesh properly? And so now we've got the idea underway, let's go ahead and hop into OneNote here. And so OneNote, what I've done is take a few screenshots of my model inside of SolidWorks. We've numbered the gears 1, 2, 3, 4, 5, and 6, just walking left to right. Also, just a little bit other information that we have. The diametral pitch of all the gears is going to be equal to 6. Pressure angle is 20 degrees. And then the next line just shows the number of teeth on each gear. So the first gear has 18 teeth, second gear 44, so on and so forth, till our final gear is the largest one with a teeth count of 60 there. Finally, our known input angular velocity is saying, hey, we've got, say, an electric motor. It's attached to the shaft, which is attached then to gear 1. It is turning at 720 RPMs in the counterclockwise direction. What is the angular velocity of gear 6? And also, what is the distance between the shafts of gear 1 and gear 6 are the two questions we're trying to ask. Also, as far as where all this information is going to come from, some of the formulas is from my Zeka's text that we're using in our kinematics class, and so you can get the reference for it right there. And so how do we go about solving this? Well, I'm first going to work on determining the angular velocity of the gear 6, and then we'll come back and worry about the center distance second. And so in order to figure out the angular velocity of that gear, well, we needed to find something called the train value. And so the train value, we'll just set that equal to the variable TV, is basically a ratio of the angular velocity of the input gear to the angular velocity of the output gear. And so I can just write that as omega in over omega out, as I believe how it's defined in the text. Well, for us, that omega in is just omega 1, and omega out is the omega 6 there, just to match up to the nomenclature we were using above. And so this is equal to the product of all the velocity ratios happening between all the individual gear meshes. And so I'm just going to walk through the train now and say what's meshing with what. And so here I've got gear 1 spinning. First thing it's going to do is mesh with gear 2 and cause gears 2 and 3 to rotate at some angular velocity. And so the first velocity ratio that I need to be able to work with is the ratio between 1 and 2. And so here I'll just call that velocity ratio 1, 2. And we'll just have a string of these that we'll have to worry about. Next we've got the velocity ratio of 3, 4, right? Because 2 is going to be spinning, 2 and 3 are on the same shafts and they're going to share the same angular velocity, so we'll know the angular velocity of 3. And then we've got 3 meshing with gear 4 here. They're kind of on the back side of the gear train, if you will. And so we'd have velocity ratio 3, 4 as the second term in this product. And then finally we've got one more, I believe. If we know the angular velocity of gear 4, that'll be the same as 5 because they are going to be on the same shaft and share that same angular velocity. And then we'd have 5 and 6 meshing to finally get us to the angular velocity of gear 6 there. And so we're really kind of daisy chaining ourselves along here in order to go from our inputs to our outputs. And so that defines the train value for us, but what is the velocity ratio? Well, we'll step over here a little bit to define the velocity ratio that's found in the text reading. Very similar to the train ratio, the velocity ratio is a ratio of the angular velocities of two mating gears, except for here, instead of having a train value where I've got multiple gears meshing together at multiple points, it's just between the two of them. And so here we'd call it omega 1 over omega 2. There's the ratio of the angular velocities. Generally, we think of the gear with subscript 1 here being the driver, and the gear with subscript 2 being the driven gear. And so there's a few different ways to express this in terms of properties of the individual gears. One is using the pitch circle, and so I can either use pitch circle radii or the pitch circle diameters. Either way, if I use pitch circle radii, it becomes R2 over R1. Or it'd probably be easier to deal with the diameters, so that would be D2 over D1, where of course the pitch circle diameter is just twice as large as the pitch circle radii. Or even more convenient would be the number of teeth. And so we could write this as N2 over N1 as well. And so fairly easy to jump from radius to diameter. That makes intuitive sense. But how do we get from diameters to the number of teeth? Well, we can look at the definition of the diametral pitch, and that it's the number of teeth divided by the diameter of the pitch circle of a certain spur gear. And so here we could solve this for n. N is equal to d, that's the pitch circle diameter, times the diametral pitch. Well, if two spur gears are going to mate properly, then the diametral pitch has to be shared between them. So it would be the same value. Essentially, I would cancel off the diametral pitch from the fraction, and we'd be just left with the ratio of the number of teeth there. And so using that, I then look up at my inputs, and the most convenient expression for the velocity ratios appears to be the number of teeth, right? Because here I've got N2 over N1, and I've got all the teeth count for each of the gears. And so here I just need to focus on, okay, I've got the driven gears number of teeth divided by the driving gears number of teeth, and I'll just write that fraction for each of the velocity ratios I've got over here to define the train value. And so first I'll come up here, okay, the train value between 1 and 2, 1 is the driver, 2 is the driven gear, so it'll be N2 over N1. And so we'll just jump down here. This is going to be N2 over N1. The velocity ratio of 3, 4. Well, that's 3 and 4 mating. 3 would be the driver, 4 would be the driven gear, so it's 4 over 3. So this will be N4 over N3. And then finally, we have velocity ratio of 5, 6. Well, 6 is the output gear, so it's going to be the driven gear, so N6 over N5. So we know the number of teeth on each of the gears, so it's just a matter of plugging and chugging here to come up with this value. And so N1 and N2, N2 is 44, N1 is 18, so 44 over 18 is my first fraction. And 4 and N3, and 4 and 3, we have 52 over 52, so that's just essentially going to be 1, but I'll go ahead and write it as 52 over 52. And N6 over N5, 60 over 20. And so let's compute this value. And so I've got 44 over 18 times 1 essentially, and then times 3. In decimal, it's 7.3 repeating, so 7 1/3. 22 over 3, I believe, is the fraction. So however you want to look at it, 22 over 3, or 7.3 repeating. Alright, so now that I've got the velocity ratio, that can be thought of as the ratio of the input angular velocity to the output. Well, I'm after the output, or omega 6 here, and so using this first part of the expression where we talked about the definition of the train value, I should be able to solve for the magnitude, at least, of omega 6. At this point, I haven't really dealt anything with whether that gear is going to be turning clockwise or counterclockwise. So I'll just say, okay, omega 6 here is omega 1 over the train value, where I have omega 1. That was something that would be known. 720 RPMs counterclockwise. And I'll divide that by the train value. The train value is going to be a dimensionless quantity there, so my output will end up being in RPMs. And that is roughly 98.18 RPMs. And so that's just a description of how fast it's spinning, right? 98.18 RPMs. But what about the direction? Is this thing going clockwise or counterclockwise? Should be the next thing that pops into our minds. And so we can go up here and do this one of two ways. One way would just be via inspection. And so that's what I'll just draw out here on the gears themselves. And so it's a fairly simplified gear train here, and so I can just basically walk my way through it. The gear 1 is turning in the counterclockwise direction, so gear 1's going this way. Now, the way spur gear teeth work, basically when they mate for external spur gear teeth, which is what we've got all here, they end up spinning in opposite directions here. And so that's going to cause gears 2 and 3 to go in the clockwise direction. Gear 3 goes in the clockwise direction as well, and so that's going to force gear 4 to go in the counterclockwise direction. And then gear 4 and 5 are on the same shaft, sharing the same angular velocity, so it's also going counterclockwise, which is finally going to make gear 6 go in the clockwise direction there. And so if I want to make a note down here, this 98.18 RPMs is in the clockwise direction. And so really that's what we were after for task 1, to determine the angular velocity of gear 6. I want to put a little box around it. It's going 98.18 RPMs in the clockwise direction. For more complex gear trains, it might be a little bit difficult to step your way through it and just do it via inspection to figure out the angular velocities. And so one rule that we have is that the velocity ratio should always be a negative number if the gears are meshing externally, as far as these spur gears go. And so let's see if we can figure that out. And so if I apply that convention, I'll do it in green here. The velocity ratios here would be a negative value here, a negative value here, and a negative value here, which would be negative, negative, negative. Well, if I've got negative times negative will be a positive, then I'm going to have a positive times negative. That would end up making this a negative value. And so now the train value would be negative. That's basically saying that the input and outputs would be rotating in opposite directions. And so if I bring that down here, Omega 1 was 720 RPMs. The direction on it was counterclockwise. Generally, we consider counterclockwise rotation as positive. And so we'd have a positive value for 720. In the denominator, now we'd have a negative value here. The result of a negative value here for the omega 6 would be interpreted also as clockwise motion there. And so that's another way to determine the direction of rotation of your driven gear in your gear trains there, is just to remember that, okay, a velocity ratio, if it is external gear meshing, is a negative value. If it's actually internal gear meshing, then it would have been a positive value there. And if you remember those simple rules and then just work through the arithmetic, then you would have the ability to detect the change in direction like we're seeing here. Again, you'd usually set up a convention also that counterclockwise rotation is considered positive and clockwise would be negative there. And so either way, it got us to a angular velocity of roughly 98.18 RPMs in the clockwise direction. And so now on to task number 2, determine the center distance between the axes of revolution of gears 1 and 6. And so by the axis of revolutions between gears 1 and 6, we're wanting this horizontal dimension between the center of gear 1 and the center of gear 6. And so one way to look at this would just be looking at how these gears mesh up. And so when these gears mesh, the pitch circle diameters would become lining right on top of each other. A better way to look at that would be the pitch circles would become tangent to each other, and so the radii would add to each other. And so I'd have this right here would be R1, and then the distance from here to here would be R3, followed by, okay, another distance between here and here would be, excuse me, I'm off for a second. This is not R3, but is R2. We'd have R2 right here. The reason I'm saying R2 is because if we look at the ISO, gear 1 mates with gear 2 here, so it'd be the sum of R1 and R2. And then finally, we'd transfer back to the back gear, which is R3. My apologies. And so we'd have R3 here. And then from here to the center distance, well, that's the meshing of 3 and 4. So this would be R4. So from here then to here would be R5. And then finally, to bring us all the way to the other end, would be R6 here. And so that would be one way we could look at it. It'd just be the sum of those individual pitch circle radii, and you just have to be careful which gears are meshing with which in order to pick up the correct relationship there. Just like I messed up slightly there at the beginning, where I mistakenly would have put R1, R3, R3 instead of R1, R2, and then R3. So to determine the pitch circle radii, we could do that through first calculating the pitch circle diameters here. You can see through the definition of the diametral pitch, and then we would just divide by 2 to come up with pitch circle radii. Another way to do it would basically be looking at calculating the center distances between each gear set, and then we would just add the 3 together because we're going to have a center distance between 1 and 2, between 2 and 5, and between 5 and 6 here, if you will. And so let's look at that way. And so these center distances we should be able to calculate using a formula just like we've just been talking about. Here I'll use blue. That's a color we haven't used yet. And so we'd have something along the lines of C external would be the sum of the pitch circle radii, R1 or I2. I could also write that as D1 plus D2 over 2, just relating the radii to diameters. Or finally, I could introduce the definition of the diametral pitch, and it would be N1 plus N2 all over 2p sub d. So N1 plus N2 all over 2p sub d there. And so let's go ahead and use that one. That's going to be the most convenient. Still uses the number of teeth and the diametral pitch that we're given here. And so first thing I'm going to look at is the center distance between gears 1 and 2. And so C12 would be equal to, that's going to be N1 plus N2. All over 2p sub d. Excuse my little bit nasty writing there. And so N1 and N2. N1 is 18, N2 is 44. So 18 plus 44, the sum there. All over 2 times 6 was our diametral pitch here. And so I'll just grab my calculator, compute that value. 18 plus 44 divided by 12. 5.16 repeating inches there for the center distance between the first and second shaft. Next we have the center distance between 2 and 5, but which gears are actually meshing together to create that? Well, it's the gear 3 and gear 4 here, and so I'm just going to call that C34 to remind myself of which gears are driving this, and so it'll be N3 plus N4 all over 2p sub d. So N3 and N4, I believe those both had 52 for the number of teeth. So just following the formula, 52 over 52 divided by 2 times 6. 8.6 repeating, so 8 2/3 of an inch here. And so we've got the center distance between 1 and 2, now between 2 and 5, if you will, and then the last one would be the center distance going from 5 to 6 here. And so 5 and 6 are the two gears that are driving that distance, so I'll call it C5, 6. And so that's N5 plus N6 all over 2p sub d. The number of teeth on 5 and 6 were 20 and 60. So 20 plus 60 all over 2 times 6. Getting slightly messy here, but we've got 80 over 12, 6 2/3. So 6.6 repeating inches. Finally, the center distance between shafts 1 and 6 will just be the sum of these. And so I'll just write here, C16 will be C12 plus C34 plus C56. And I'll just enter that into my calculator. And I am arriving at 20.5 inches here as the result there. And so what does this mean? Well, the distance you'd space the shafts between 1 and 6 would be 20.5 inches. Between 1 and 2, we've already calculated as 5.16 repeating. Between the 3 and 4, 8.6, and between 5 and 6, 6.6 there. Summing them all together to get 20.5 all the way from the left to right of the centers of the axes of those shafts there. And so boxing that one off as well. And so there you have it. I think we've got both of the values we're looking for. We've got the angular velocity of the final driven gear, as well as the center distance between the far left shaft and the far right shaft, as well as all the intermediate shafts there as well. And so thank you for watching the video. Hopefully this helps you with understanding how gear trains operate. And I'll probably make a second video where we'll do a little bit of this in SOLIDWORKS to see if we can run a SOLIDWORKS motion study to help us validate this. And so, as usual, thank you for watching the video.